Hello everybody. Today we're going to finish up our discussion of significant figures. And in this one we're going to be looking at the answers. We've already talked about what significant figures are and why scientists need to deal with them when they're talking about measurements and data, and how to look at data and determine which ones are significant figures and which ones aren't. But the last thing that we need to deal with then is, what about an answer that you calculate based on significant figures? The problem with significant figures is that calculators don't really get significant figures. Suppose you want to calculate the density of something, and it's got a mass of 28.3 grams, and you've measured the volume to be 19.81 cubic centimeters. Since calculators don't really understand significant digits, when you type in 28.3 divided by 19.81, it's just going to keep on spitting out digits until it runs out of space to show them. In fact, I typed this in my calculator just a minute ago, and this was the answer that it shows me. Now, if you look at that, you should realize pretty quickly, well, that answer is showing an awfully high degree of accuracy. There's like 16 or 17 significant figures shown in that answer. But the data that we used to calculate it wasn't anywhere near that accurate. That means that most of those digits in that number are just garbage. They're just meaningless. So we need to be able to figure out where we should round that answer so the answer shows only the significant digits, only the digits that have meaning. Now, when you do this for multiplication and division, it's a little bit different than you do when you're adding numbers. So we're going to go through both of them. For multiplication or division, what you do is first you look at the factors that were involved in the calculation, and you determine the number of significant figures in each factor. So in this case, our two factors are 28.3 grams and 19.81 cubic centimeters. When we look at those, we can see that the 28.3 grams is only accurate to 3 sig figs, and the 19.81 was actually accurate to 4 sig figs. So we know that those two data points have different degrees of accuracy. So if we calculate something based on those, what we do is we just say, well, we've got to round the answer so that it has the same number of significant figures as the factor that had the fewest. Again, remember that your answer can't be any better than your worst factor. Well, in this case, our worst factor only had 3 significant figures, which means our answer needs to be rounded at 3 significant figures. So we look at this number that's showing up on the calculator, the 1.428, etc., and we just start at the left and count our significant figures. Well, the 1 is the first one, the 4 is the second one, that 2 that's out there in the hundredth spot is our third significant figure. That's the point where we need to round this thing off. So we look at the 1.42, the digit after that 2 is bigger than 5, so it tells us we round up. So this density, when we round it to correctly, would be 1.43 grams per cubic centimeter. Again, all those other digits that are showing up on the calculator, those are just meaningless. Those are garbage. Now, what do you do if you've got something where you've got to add some numbers? Well, when you're dealing with data and you've got to add the values up, you do your rounding first this time. So suppose we've got these 3 numbers, these 3 distances, and we need to add them up. We've got 3 things. One of them is 1.03 or 103.6 meters long. Another one's 35.064 meters long. Third one's 1.00694 meters long. So you can see each one of those measurements were made to differing degrees of accuracy. When you're adding them, you do your rounding before you do the math function. So here what you do is you look at your factors and you round them so that they're all the same degree of accuracy. That means you have to figure out which one is the least accurate and round them all to the same degree of accuracy as your least accurate. Well, up in our measurements, the 103.6 meters is accurate only to the nearest tenth. The second factor is out there accurate to the nearest thousandth of a meter, and the last one is out to the nearest, 100,000th, 10,000th of a meter. And so the 103.6 is our least accurate measurement. So we go through and we take each one of those factors and we round them so that they're at the same degree of accuracy. It means we round them all to the nearest tenth. When you round those off, that's 103.6, 35.1, and 1.0 meters. Now, the rounding has already been done. Now we can grab our calculator, draw a line and add, type it in, and we find that our answer is 139.7 meters.